Here are some notes on section 6.5, and let's go back and take a look at what we did in 6.4. We talked about the rate of change of a population, and when the rate of change of a population is directly proportional to the size of the population grows exponentially. So mathematically speaking, we could write this like this: the rate of change of the population is directly proportional to the population. In other words, as the population goes up, the rate goes up. And there's a constant of proportionality we usually have to find, and that's going to be positive when we have growth. Okay, so this is the fact that the rate of change is proportional to the population. And that really implies that when we solve this differential equation, separated the variables and solved it, we got this equation, which is the exponential equation. It shows that it's exponential growth. So whatever my initial population is, it's going to grow e to the kt. K will be the constant we figure out over here, and t is time. So it's going to be exponential growth. Now, look in your books on page 362 and read this, how population grows. Okay, it says in section 6.4, we showed that when the rate of change of a population is directly proportional to the size of the population grows exponentially. That's what we just said. This seems to be a reasonable model for population growth in the short term, but population in nature cannot sustain exponential growth for very long. Available food, habitat, living space are just a few of the constraints that will eventually impose limits on the growth of any real world population. In other words, we just can't keep growing exponentially because eventually we're going to run out of space or run out of food, etc. So what happens? Well, we have to have some kind of limiting factor. In other words, it's just so big the population can get. In other words, the planet Earth, as an example, is going to hold just so many people. It's not unlimited. And that number that it will hold, that it will be able to support as far as food, air to breathe, water to drink, and actually space to occupy, that would be our limiting factor. So in section 6.5, this is what we're talking about when we talk about these logistic differential equations. If we want the growth rate to approach zero as P approaches a maximum carrying capacity M is the carrying capacity, that's the constraint, that's how big the population can get, we introduce a limiting factor of M minus P. So, in other words, here's our exponential growth, but, all right, as my population gets closer and closer to this limiting factor, M, then this factor is going to get closer and closer to zero, and that's going to make this smaller. So as P gets bigger, this is a constant, okay? M's a constant, that's R carrying capacity, and K is a constant. So I don't know if I said that someplace, but I should have said that M's a constant and K is a constant, positive constants. Okay, so as this is a constant, as P gets bigger, this number gets smaller and smaller and smaller. So as P approaches M, as P gets closer and closer to M, then this is going to get closer and closer to zero, and my growth rate will get closer and closer to zero. So this could be your population, and as I will increase till I get to a certain point, then I'm still increasing, but I'm slowing down, and my population is approaching this carrying capacity M. This is the population. So I'm going to grow very, very fast for a while, then all of a sudden, this limiting factor will take effect, and then it's going to start to slow me down. Okay, so if you can see that, and you can see that the growth rate, dp dt, if this is a population to time graph, the growth rate is the slope of this curve. So here, my population starts growing slowly and gets faster and faster and faster. Right about here, it's the steepest. So that's probably where my growth rate is the greatest. And then it starts to slow down as the population gets closer and closer to M. This starts to get closer and closer to zero. This gets smaller and smaller and smaller, which makes this smaller. So it slows things down until eventually, as I get really, really close to the population, this is very, very small, and it starts making everything get smaller. So eventually it's going to be zero. So when these are the same, this is zero, and I can't grow anymore. because I've approached my limiting factor. So this is what you want to read, and this is the graph of the population, and this is my logistic differential equation. And it has this growth factor in there, M. M is what we would call the carrying capacity. Okay? So kind of read this and take a look at it so you have an idea of what's going on. If we didn't have this carrying capacity, my population would just be getting bigger and bigger and bigger. It'd just go up like this. All right. But in nature, that can't happen. We'll run out of room. So we'll start growing exponentially. Then we get to this point, then we start to slow down. And basically, you can see our curve here is concave up, then it's concave down as I approach it.